Welcome back to AS Chemistry. In this theme 1.3, we'll explore chemical bonding. You'll learn about ionic, covalent, metallic, and coordinate bonds, electronegativity, molecular shapes, and intermolecular forces. These concepts explain how atoms connect and why substances have their unique properties. Let's begin. Electronegativity and polarity. Electronegativity is the ability of an atom to attract electrons towards itself. Smaller atoms with stronger nuclear pull have higher electronegativity. Across a period, electronegativity increases. This is because atoms become smaller and nuclear attraction becomes stronger. Down a group, electronegativity decreases as atoms get larger and nuclear pull weakens. When two atoms with different electronegativities bond, they create a dipole. One atom becomes slightly negative and the other slightly positive. The greater the difference, the more polar the bond is. If the difference is very large, the bond is almost ionic. Exam tip: always link bond polarity to differences in electronegativity. Questions often test this connection. Ionic bonding. Ionic bonding is the strong electrostatic attraction between oppositely charged ions. Ionic compounds form giant lattices, which are crystalline solids. They have high melting and boiling points because a lot of energy is needed to break the lattice. For example, in sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion by 6 sodium ions. This is called the coordination number. Worked example. Explain why magnesium chloride has a higher melting point than sodium chloride. Answer: magnesium forms a 2+ ion, while sodium forms a 1+ ion. The greater charge means stronger electrostatic attraction in magnesium chloride, so more energy is needed to break the lattice. Exam tip: when asked about ionic properties, always mention lattice structure and electrostatic attraction. Covalent bonding. Covalent bonds form when atoms share pairs of electrons. The shared electrons are found in orbitals between the two nuclei. Each covalent bond involves one pair of electrons. Some electrons are not shared. These are called lone pairs. Lone pairs affect the shape of molecules by repelling bonding pairs. Covalent compounds often have low melting and boiling points because their molecules are held together by weak intermolecular forces, not strong bonds. Special note: elements in period 3, such as sulfur and phosphorus, can expand their octet. For example, PCl5 and SF6 have more than 8 electrons around the central atom. Coordinate or dative covalent bonds. A coordinate bond is a type of covalent bond where both electrons come from the same atom. The atom that donates the electrons is called the donor. The atom that accepts them is the acceptor. For example, the ammonium ion forms when ammonia donates a lone pair to a hydrogen ion. Another example is aluminum chloride. At high temperature, it exists as AlCl3, but as it cools, it forms a dimer, Al2Cl6, using coordinate bonds. Metallic bonding. Metals bond through metallic bonding. This is the attraction between positive metal ions and delocalized electrons. The structure is a lattice of cations in a sea of mobile electrons. The strength of metallic bonding increases with higher charge on the ions, smaller ionic size, and more delocalized electrons. That's why magnesium has stronger bonding than sodium. Exam tip: metallic bonding explains why metals are good conductors and malleable. Always mention delocalized electrons in your answers. Shapes of molecules. VSEPR theory. The shape of a molecule depends on the number of electron pairs around the central atom. Electron pairs repel each other and arrange themselves as far apart as possible. For example, carbon dioxide is linear with a bond angle of 180 degrees. Boron trifluoride is trigonal planar with 120 degrees. Methane is tetrahedral with 109.5 degrees. Ammonia is pyramidal with 107 degrees. Water is bent or angular with 104.5 degrees. More electron pairs mean different shapes, such as trigonal bipyramidal and octahedral. Exam tip: always state both shape and bond angle when asked. Hybridization. Sometimes orbitals mix to form new hybrid orbitals. For example, sp hybridization forms linear molecules like carbon dioxide or ethine. sp2 hybridization forms trigonal planar molecules like boron trifluoride or ethene. sp3 hybridization forms tetrahedral molecules like methane or silicon tetrachloride. Hybridization explains why bond angles are not random but follow a predictable pattern. Bond energy and bond length. Bond energy is the energy needed to break 1 mole of a bond. Bond length is the distance between the nuclei of 2 bonded atoms. Shorter bonds are stronger because the electron density between the atoms is greater. For example, a double bond is shorter and stronger than a single bond. Intermolecular forces. Between molecules, there are weak forces. These include van der Waals forces, permanent dipole interactions, and hydrogen bonding. Van der Waals forces exist between all molecules, but are especially important in nonpolar ones. They become stronger as the number of electrons increases. Permanent dipole-dipole forces exist between polar molecules. The partial charges attract each other. Hydrogen bonds are the strongest intermolecular force. They occur when hydrogen is bonded to fluorine, oxygen, or nitrogen, and is attracted to a lone pair on another molecule. This explains why water has unusually high melting and boiling points. Exam tip: be ready to compare intermolecular forces. For example, explain why ethanol boils at a higher temperature than ethane. The key is hydrogen bonding. Polar and nonpolar molecules. Polar molecules have unequal sharing of electrons, so they have partial charges. Nonpolar molecules share electrons equally or are symmetrical, so their charges cancel. Carbon dioxide, although it has polar bonds, is a nonpolar molecule overall because it is linear and symmetrical. Closing recap. In this chapter, we've covered the main types of bonding: ionic, covalent, metallic, and coordinate. We've looked at molecular shapes, hybridization, bond strength, and intermolecular forces. Chemical bonding is central to chemistry because it explains the properties of substances, from salt crystals to metals to water. Master these concepts and you'll have a strong foundation for the rest of the course.